Now let's continue our talk on graphing rational functions and expand on what we started on the last video about horizontal asymptotes. Horizontal asymptotes are dependent on degree, so you want to look at the degree of the top and the degree of the bottom, or the numerator and the denominator. And if the degree of the top is greater than the degree of the bottom, then there will be no horizontal asymptote. There could be a slant, or it's also called an oblique asymptote, and we'll do those on another video called slant or oblique asymptotes. But you can say for now there's no horizontal asymptote. Then if top degree is less than the bottom degree, and we're talking about degree here, not the coefficients, but the degree on the x, you will have a horizontal asymptote at y equals 0, which happens to be the x-axis. Then if the top degree equals the bottom degree, you'll have a horizontal asymptote at y equals a over b. A being the top leading coefficient and b being the bottom leading coefficient. And we did that on the previous example on the other video, where the top leading coefficient was a 1 and the bottom leading coefficient was a 1, and so we put 1 over 1, and that was y equals 1, and y equals 1 was the horizontal asymptote. They won't always be 1s, they could be all different numbers, and we'll see in our 3 examples below. So in these 3 examples, let's first determine which is bigger, the top or bottom degree. So the top degree is 2, the bottom degree is 2. It doesn't always have to be the one in front, because it may not be written in standard form, but you look for the highest degree in either the top or the bottom. And then, so this would be that the top degree is equal to the bottom degree. The second scenario, you have x to the first, so it's a degree of 1, and x to the second on the bottom, degree of 2. So the top degree is less than the bottom degree. Then on the third example, the top degree is greater than the bottom degree. So that's what the 3 scenarios would look like. Now let's find out what the asymptotes are. So on example 1, our leading coefficient of this leading term is a 2. And so that would be our A. And our B would be the leading coefficient of our leading term, which if we put it in standard form, that negative 3x squared would be our leading term, and you put that coefficient down on the bottom. And so y equals the top coefficient over the bottom coefficient is your horizontal asymptote. And so negative 2/3, you can move that negative out from the bottom and put it out in front, but basically y equals negative 2/3 would be the horizontal asymptote. On example 2, the top is less than the bottom degree, and so that puts our horizontal asymptote at y equals 0 every time. Anytime the top degree is less than the bottom degree, our asymptote is y equals 0. Does not matter what the coefficients in front of these are, even though they're 1s, that has nothing to do with it. It's just always y equals 0. Then on number 3, the top degree is greater than the bottom degree, and so there's no horizontal asymptote, and there might be a slant asymptote, but we'll discuss that later. Here's an important rule to write down, and it has to do with vertical asymptotes and what we call holes. And both a vertical asymptote and a hole is called a discontinuity. It's basically, instead of the graph being some continuous curve, there is some kind of break in that continuous curve, and it may be that they end up like this, where there's an asymptote, or it could be that it's just some kind of graph that has a hole in it, and in that hole would be a missing point, and so that would be considered a discontinuity as well. Something that always continues forever and ever and has no break in it is called a continuous graph. A discontinuity is where it's not continuous, and that can occur where there's a vertical asymptote or where there's a hole. So let's talk about these scenarios. So I went ahead and factored the rational function for you already. And when you have a rational function, I mentioned this in the first example on the first video, that you always want to look to see if any of the factors will divide out or cancel out. And in this case, there is a factor that will divide out, and basically these just are dividing out to ones, and they can end up being dropped out. And so what we end up with is a new function that is y equals x plus 1. Now that is an equivalent expression to the original expression as long as we know that x cannot equal whatever would make the denominator 0, which in this case would be a 4. A 4 would be the x value that would cause the denominator to equal 0. So these graphs will look almost exactly alike. It will look like this as long as you leave a hole where x is 4. So let's look at what that looks like. If you look at this equation or function, that is just linear. It's a line. It's going to fit the pattern y equals mx plus b. And so our b is our y-intercept, and that happens at 1. And so our line will cross through the y-axis at 1. And then our slope is 1, which we could put over 1, so we have a rise over run. And so you go up 1 over 1, up 1 over 1, up 1 over 1. And you can see what our line looks like. The problem with this is that the original equation or function was not just y equals x plus 1. It was actually this whole rational expression. But the interesting thing is the only difference between those two is this hole. It will look like that line, except there'll be a hole when x equals 4. And so where that hole will show up is wherever the x is 4. So you go to where x is 4 on the graph, and x is 4 about right here. And so at that spot where x is 4, you will have no graph there. So let me fix this up a little bit. We're going to continue this line forever, but we're going to have a hole in the line right there. And so there will be no point at that specific point, and the only way you can really show that well is to draw an open circle, meaning there's a hole there. And so that is literally the graph of this function. It looks almost like its simplified function, except for the fact that you have a hole at x equals 4. And one thing you want to notice is it's only a hole when that factor cancels out. If it didn't cancel out and it was just on the bottom, that would cause a vertical asymptote, not a hole. It has to do the canceling out thing for it to be a hole, and then you can graph this simplified version of it and just make sure you put the hole in it. Here's another example, and I wanted to make a point here that this denominator cannot factor, and there's no way to make it equal to 0. If you did make this equal to 0, you would get imaginary numbers. So you would get x squared equals -1. You could square root both sides, put a plus or minus here. X would equal plus or minus the square root of -1 is just I. And so that is not going to show up on the graph because it's imaginary. And so this one, there's no way, there's nothing you could put in for x to make that denominator equal to 0. So what that means is the domain is all real numbers. And because the domain is all real numbers, there will be no discontinuities. It will be continuous. And this one makes a really funky shape. It comes in like this, and then it kind of dips down and touches this, and then it goes through there and does something like that. And the interesting thing is you could look at this and say that y equals 0 is the horizontal asymptote, but it's not an asymptote for the whole thing. It's only an asymptote for the left piece, and that's kind of a tricky one that we don't need to worry a whole lot about right now. But this ends up getting closer and closer to that asymptote as we move to the left. But as we move to the right, there is an actual x-intercept, and so it rises above the x-axis on the right side. And so that kind of breaks the rules a little bit on the horizontal asymptote, but the main thing you need to notice here is from side to side, there are no breaks in this graph, and so it is continuous. The last example I wanted to show you is one that has a horizontal asymptote, a vertical asymptote, and a hole. So let's start by factoring this rational expression. Now you can see that there is a factor that can be divided out, and that will cause a hole. So we know a hole will happen wherever that factor equals 0. And so that hole will happen at -4. But in addition to that, there's still another denominator piece that does not cancel out, and that will cause an asymptote. So whatever would cause x minus 4 to equal 0, which is x equals +4, that will be your vertical asymptote. Finally, we'll have a horizontal asymptote, and if we look at the leading terms, their coefficients are 1 and 1, and when the degrees are the same, x squared and x squared, the degree is 2 on each of them, then you put the 1 over 1, and that becomes your horizontal asymptote. That's only when the degrees are the same. So I've written the two asymptotes, the vertical asymptote and the horizontal asymptote, and then I just made a little mark right here to remind myself that at wherever x is 4, that part of the graph will get a hole in it. You'll also notice I made a table here. Now you could fill the values in that I just chose some random values for x, and you could fill those into the original function and get your y values, or you could look at your graphing calculator table as well. So we're going to fill in these values. That will help us with the general shape. So at -1, we want to go up 4/5, which is really close to 1. And then at 0, we want to go to 3/4, which is a little bit lower than that. And then at 3, we want to be at 0. And then at 5, we want to be up at 2. And at 6, we want to be up at 3/2, which is 1.5. And so that comes down a little lower than the one before. So what that helps us to see is that we're going to go like this, and then there's an asymptote, so we must have to go down, getting closer to that asymptote. And then here, we're going to get close to the vertical asymptote and close to the horizontal asymptote. And then we can't forget about our hole, and our hole happens wherever x is -4 on the red graph, and so there'll be a hole right there.